Hi, I am Alvaro Parra from the School of Computer Science of the University of Adelaide. And now I am going to present our paper, Rotation Coordinate Descent for Fast Globally Optimal Rotation Averaging. Rotation averaging plays a crucial role in computer vision and robotics in problems as visual SLAM and structure from motion. In this example, starting from random initial rotations represented as black arrows along the camera trajectory, our method, RCD, found the optimal orientations in less than 2 seconds, from which an structure from motion method produced the final reconstruction. Let me introduce rotation averaging through a simple example with 5 cameras. Let R1 to R5 be the absolute camera orientations we want to find. We connect two cameras if a relative rotation measurement can be established between them. For example, R tilde 1, 2 is the relative rotation of camera 2 with respect to camera 1. R tilde 2, 3 is the relative rotation of camera 3 with respect to camera 2, and so on. This is the camera graph. In the ideal case where there is no noise, relative rotations are consistent with the absolute ones. Since we have noise in real life, we aim to find absolute rotations that minimize inconsistencies over all the measurements in the camera graph for some distance function and usually p equal to 1 or 2. We can compactly rewrite the problem for the caudal distance and p equal to 2. Here, Ti is the trace, R contains the non-absolute rotations, and A tilde is a symmetric matrix encoding the noisy measurements that are present in the camera graph. Our problem is non-convex because of the non-convex domain of rotations. However, through Lagrangian duality, we can obtain an SDP relaxed version. Erickson et al. Proved that under mild conditions on the noise level of the measurements, the strong duality between these two problems holds. Hence, we can solve an equivalent convex problem. Let me describe one iteration of RCD. First, we set a camera as the origin, for example, the first camera. As our problem is convex, we can start from any initial solution without affecting convergence. We set W as the first column of R tilde as we pick the first camera as the origin. If we were chosen the second camera, then W should be the second column, and so on. Similarly to the BCD method introduced in Erickson et al., we produce Z from the current solution and W. However, since we manipulate rotations instead of a dense, positive, semi-definite matrix, this operation is order n rather than n squared. The update is computed efficiently in closed form involving solving the SVD of a 3 times 3 matrix. Finally, we update the rotations from orthogonal matrices by flipping the determinants if needed. We mathematically prove the convergence of RCD. Each iteration set a new origin and update all rotations such that the objective decreases. Since we keep valid rotations, we also propose RCDL, which uses a local method to speed up convergence. This example with 5,000 cameras demonstrates the effect of local optimization on the convergence of RCD. The figure plots the objective value for RCD and RCDL at increasing epochs, where an epoch is equal to the number of cameras. We observed that during the first epoch, the local algorithm drastically reduced the objective. This jump of the objective value reveals the collaborative strength of global and local methods, which enable RCDL to converge in much fewer epochs compared to RCD. Experimentally, we show superior efficiency over state-of-the-art global methods on a variety of problem configurations. For example, RCDL is over 3 times faster than shown on averaging in this Torus example with 5,000 cameras. For this structure from motion example, RCD was more than 47 times faster than shown on averaging, finding the optimal camera orientations in less than 0.8 seconds. We have significantly outperformed state-of-the-art global methods on a variety of problem configurations. Moreover, RCD is simple to implement. Please check our paper for more results and details. I also invite you to visit our project website from where you can download the source code and demonstrations. Thank you.